So I want to show you some problems I did out of a calculus book, just to, think about this a little bit more. I chose 3 problems just to do, really quickly, and I decided to do a video about them because it's kind of interesting. So the first, we have 3 functions here. The first one is f of x equals 2x squared minus x cubed. And as I zoom up to this one, they're looking for the area, as this curve, it kind of goes to 0 and then kind of increases. So we have this nice area to calculate from 2 to 1. From x equals 2 to x equals 1, they want the area of this pink shaded area. So it's going to come out like this. That's the thing we're going to have. The definite integral of 2 to 1 of 2x squared minus x cubed dx. And as we know from the fundamental theorem of calculus, that we're just going to do f of 3 minus f of 1, and that we took the antiderivative of each term here, and then we plugged in the numbers, eventually getting about 4/3 for the area of that shaded area, for the area of that shaded part. And secondly, we have the curve, which is non-continuous, of the square root of 1 plus 3x, and it just kind of comes out of the x-axis and, grows. So they want the area from 8 to 1, and this obviously isn't drawn to as much scale as it should be, but, they want the area, the definite integral from 8 to 1 of the square root of 1 plus 3x dx. Same thing here. We get the antiderivative of this, which sometimes I do I like figure out the antiderivative, and that's kind of not a simple thing. It really is not that simple, because I think finding the derivative is more simple than finding the antiderivative. So sometimes I cheat when I see a antiderivative that is kind of difficult. Like the trig functions, the antiderivatives of that are pretty simple. There are rules as to how those work, rules for derivatives and for antiderivatives as to how the trig functions work, of doing that. So that's pretty simple. And as stuff like this, 2x squared, that's pretty simple via the reverse power rule, which is this. It's that. Say we have x squared, the antiderivative of that is x to the 3rd over 3. That's simple. But stuff like this, and like I said, the antiderivative of these two, and this, pretty simple. This is not. So that one I ended up looking up. So, simple again. Once you have the antiderivatives, you plug it in, and the area of this little shaded area happens to be 26. And this is an interesting one because we have a sine curve, which is sine of x over 5, and they want the area from -3 to 3. And as you can see, we have a area of negative area here. It goes below the x-axis there. Therefore, it's a negative area. So it's interesting how this one came out, I think. I mean, it was for me, because I'm still kind of grasping this stuff. So I'm not, claiming to know anything about it. And fifth, there's 5 pi here, which is like 15, something like that. And pi over 2 is like 1, given the unit circle. You learn that in trigonometry. So they want the area from -3 to 3. So we have a portion that's above the x-axis, therefore it's positive area, and a portion that's below the x-axis, which is negative area. Same thing, which is pretty simple as to how you get the antiderivative of that. And same thing, you plug it in, and you end up getting -5 and -5, and a negative minus a negative, or -5 minus a -5 ends up being 0. And why does that happen? Because we have the same amount of area, we have the same amount of space above the x-axis and below it that we're calculating, therefore it's going to come out to be 0. That's what the area is going to come out. It's going to come out to be, and I think that's pretty interesting.